Today, on how it's made. Deep cycle batteries. A power trip. Tins. It's a can-do approach on this production line. And optical lenses. Making them is a matter of focus. We bring you a special two-part report. A deep cycle battery is what you find in such vehicles as trains, boats, RVs, and forklift trucks. Whereas a car battery provides a quick surge of current to start the engine, a deep cycle battery provides a steady amount of current over a long period of time. Deep cycle batteries range from 2 to 48 volts. Their power is generated by cells, a group of lead plates coated in lead oxide and acid. This casting machine produces lead grids that will become the plates in the power cells. The machine pours molten lead into grid-shaped molds. Water circulating through the mold hardens the metal in just 5 seconds. The machine casts two types of grids, negatives and positives. The next machine coats the grids with a chemical paste that contains lead oxide and acid. The positives get one paste formulation, the negatives a different one. The grids are now called plates. Workers stack them in cases, alternating positive and negative, then drop them into tanks of sulfuric acid to charge. The lead oxide and acid in the paste store the power. After charging for 24 to 72 hours, depending on the model, the plates go into a machine that washes them 3 times to remove acid residue, which, if left, would corrode the metal. The charging process blackens the plates, which are now called dry charge plates. A machine wraps each positive in glass strand matting, an insulation material similar to fiberglass, then in a plastic envelope. These coverings protect the plates from short circuits. Workers stack the plates again. Positive, negative, positive, negative. This time, though, each stack contains a specific number, from 5 to 33 plates, depending on the battery model. Each stack will become one cell. A cell provides 2 volts of electricity. Each plate has a tab. A robotic machine cleans the tabs with a wire brush and a chemical solution called flux. Then it dips the tabs in molten tin. This tin coating will improve the bond when they solder the tabs together. The robot wipes the tabs on a flux-imbued sponge to clean their surface once again, then drops the cells into a mold containing molten lead. This solders the tabs together, bonding the plates within each cell. The process casts 2 lead posts on the cell's positive side and 2 on its negative side. These posts will connect the cells and build the required voltage. Next, each cell goes into a polypropylene casing called a jar. They test each cell to make sure it functions. This also shows if the cell is positioned correctly in the jar, so that the positive and negative signs on the cell cover will be on the corresponding posts. They heat seal the cover and seal the protruding posts with lead. To test the seals, they pump air into the cell, then brush soapy water over the cover. Any bubbles indicate a gap to be resealed. In another part of the factory, workers manually mold various small components from molten lead. Among those parts, the connectors that link one cell to another. Workers weld them to the posts. These are 8-volt batteries, so for each one, they connect 4 cells inside a polyethylene case. Now that assembly is complete, the case cover goes on. These rubber grommets keep water from seeping inside and shorting the battery. Now they fill the inside with sulfuric acid, which functions as an electrolyte, the medium that helps the lead in the plates conduct electricity. The tin can was invented back in the 1800s to preserve and protect. We still rely on this trusty container to keep a range of perishables fresh, everything from food to blood plasma to military supplies. And after all these years of use, the tin can still has an airtight reputation. It's time to lift the lid on this traditional container and get the inside story from the factory. To make a tin, they take a strip of tin steel and weld it to join the ends. The resulting cylindrical shape is the body of the tin, and it's about to be hermetically sealed. The rotating tools on this machine stretch out the edges of the cylinder, forming a flange. They top off the tins at this station, where a spinning head presses the cylinder into these lids. It simultaneously rolls the flanged edges together to make an airtight seal. This container is for classified military use. But over on another production line, they're making a more standard tin, the kind you would put coffee in. So this assembly is more mechanized. In a fraction of a second, an automated welder rounds and joins metal to create the body of a tin. The tins travel forward and upward on a magnetic conveyor system. They're going to the other side of the plant, where they'll get tops and bottoms. This kind of tin has a reusable slipcover lid and gets some decorative work. Like a big cookie cutter, a punch press cuts out designs that have been pre-printed on metal. At the same time, it pushes the cut design onto a die to form the lid shape. A magnetic conveyor pulls them forward and flips the lids to stack them for packing. Elsewhere in the plant, they're making cans to go with some other lids. A lineup of circular blades slices through tin sheets. The cut pieces accumulate in stacks. They load the flat pieces of tin into a cylinder where they're curled into tubes. As they exit, robotic arms make seams in the rolled tins and a press applies force to lock them. This lock seam is an alternative to the welded one we saw earlier. Now, another magnetic conveyor pulls the tin tubes forward, and they go for a spin while rollers flange the edges so that the bottoms can be attached. Then, a punch cutter makes the bottoms, making sure to recycle the scraps. The can bottoms spin out of the punch cutter before landing on the next magnetized conveyor. They get a squirt of liquid rubber, which will harden into a gasket to prevent leaks in the can. A folding machine now locks the bottoms to the tubes as they spin. More than 12,000 cans per hour can be made on this high-speed line. From a blank piece of steel to a very useful container. Whatever their contents, these tins are destined for a full life. That is, until someone decides to empty them. It's time to turn our camera's eye on the camera's eye. Optical lenses are really several lenses combined into a single unit. Together, they recreate an image by bending light rays so they converge into a common point, called the focal point. You get the picture. These television lenses start with a very precise design. A diamond blade slices up a block of specially selected optical glass, while coolant prevents the blade from burning it. The slices then go under a diamond drill, which cuts several puck-sized discs from one glass slice. The operator is careful to keep waste to a minimum. Optical glass costs up to $1,000 per kilogram. During the drilling, the optical glass sits on a thinner piece of glass covered with wax. As the wax is melted, the discs are easily pulled away. Next, a device spins one of the discs while a wheel overhead sculpts it into a lens. The operator checks each lens for chips, and this one looks smooth. This tar-like substance is called pitch. The edges of the lenses have been built up with tape to contain the pitch. They completely coat the underside of the lens with it. Several pitch-covered lenses are now in a metal shell. A worker picks up a hot aluminum dome called a blocking body. He presses it onto the pitch-covered lenses, and the pitch melts onto it. Dousing it with water causes the pitch to harden, sealing the lenses to the blocking body. The blocking body is now upside down and acting as a holding device as it oscillates on a spinning grinding shell. The grinding makes the surface of the lenses uniform and smooth. They place a polisher on the lenses. It's lubricated with a very fine abrasive. For about an hour, the polisher oscillates while the block spins. Polishing makes the lenses smooth and transparent. It also gives them an even more curved profile. The lenses have been removed from the block, and it's time to cut the diameter down to size. Using a microscope, a technician centers a lens between two brass chucks. A diamond blade at the back cuts the lens as the technician monitors it. He's making sure the diameter and axis of the lens have a common center. Next, they group some lenses on round racks called planets. Their universe is a vacuum chamber. The technician closes the door, and the planets continue their orbit. Inside this vacuum, an electron beam evaporates coating materials. The vapor rises to give the lenses a protective coat. A computer monitors the rate of evaporation and the coating. But there's much more to come. Up next, this process really gets visual as all the pieces of a camera lens come together. The optical lens is the ultimate image maker. Along with cameras, you'll find them in projectors, microscopes, laser scanners, X-ray equipment. They give us a close-up view of so many things, it seems only appropriate that we take a close-up look at the optical lens itself. The lenses have just spent 3 hours getting a protective finish. It's time to wipe away any residue and make sure they're perfect. This particular lens is concave. She covers it to protect it while she cleans and inspects the lens with the opposite profile, convex. Then the convex lens goes to another technician who places it in a holding device. He looks into a microscope and adjusts the position of the lens until it's optically centered. He uses wax to keep the lens from shifting in the holding device. They give the lens another cleaning. Each one must be absolutely spotless before they proceed to the next step. Otherwise, dust particles could become trapped within the optical system and affect image quality. Now that the surface of the convex lens is immaculate, she dabs optical cement onto the center of it. She gives the other concave lens a little more scrutiny before she cements it onto the convex lens. She applies pressure to spread the cement between the two lenses. Cementing them together means they'll be less likely to shift around in the lens barrel. She checks for dust one more time. Then it's under the microscope for an optical alignment of this double lens. Because the cement isn't yet dry, he can push the top lens around and adjust its position. Next, they prep the barrel that will hold the lenses. The technician traces out lettering using a stylus, attached to a sharp tool that engraves information onto the lens barrel. It prints technical details that will tell the photographer just what the lens will do. Things like focal length, the f number, and the size of the aperture opening. These reference points allow the user to pull a picture into focus at the desired magnification. Now they double-check the design for this complex optical system and begin to pull all the pieces together. This singlet, or single lens, goes into the metal barrel first. Other lenses with various curvatures and dimensions follow. She places metal spacers between the lenses to separate them. Proper spacing will prevent aberrations in the image, such as blurring. Between installations, she covers the barrel with a piece of lint-free plastic because eliminating dust continues to be a necessity. One fleck could ruin this entire assembly. Using tweezers, She coaxes the last lens into the barrel. She installs a retaining ring to hold the stack of lenses down. Then she locks it into place. There's one final inspection. She examines the assembled optical lens from all angles. It takes a total of 6 weeks to make one of these optical lenses. And in the end, it's picture perfect.